turns out that just like up there, you see space and time differ by a minus sign. If you want to calculate proper time, the formula is the proper time squared is now delta t squared minus delta x squared. And if I solve this for delta tau, I, of course, get that delta tau is the square root of delta t squared minus delta x squared. Or in other words, the square root of 1 minus, well, let's write this out here, delta x over delta t squared times delta t. Or finally, the square root of 1 minus v squared delta t, which is the time dilation formula we'd all said we'd seen before. Okay. So I think that's probably all the time I can spare for this. But the idea was to convince you that even if you've only seen special relativity in a form that looks like this, okay, all the formulas you know about how distance and time transform between reference frames can really be encapsulated in this relation, or the one that looks the same, up to a minus sign, that relation, okay, which tells you how proper time and proper distance are related to changes of coordinates. Okay. So, does that catch people up a little bit? A little bit. Okay, great. All right. So now, if having agreed that this equation captures the fundamental description of Minkowski space, okay, let me just do one small thing to change this from a discussion of special relativity to a discussion of general relativity. And what I'm going to do is I'm still going to describe Minkowski space. I'm not going to curve the space-time yet. But I want to consider not large changes in distance and time, but I want to consider what happens as delta x and delta t become small, as these changes go to 0. Or more precisely, I want to consider what's known as the infinitesimal form of that equation, where I replace finite changes in x and t by the differentials dx and dt. So we simply go from algebra to calculus. Okay? So there we learn that if I have a tiny bit of proper distance, its square is given by dx squared minus, always write the dt first, minus dt squared plus dx squared. Okay, where if it is not obvious to you what this means, we will see it illustrated in an example in a few moments. All right. So this is the fundamental equation from the point of view of general relativity, if you like, that describes Minkowski space. Now, the reason I'm starting here is that what I want to show you today, in case you haven't seen this before, or in more detail than you've seen it before, is that Minkowski space, good old familiar, empty, translationally invariant Minkowski space, contains a feature which is very much like the black hole we were discussing before. And so if you can understand in detail how this works in Minkowski space, then you'll have the intuitive idea of how it works in the black hole. Okay? So, what's going on here? Well, what I really want to point out to you, in a language that will become clear in a moment, is that Minkowski space has a horizon. Now, I am not going to bother to define horizon for you in great detail, but I will show it to you. We'll see that it has the properties you've heard of for black holes, and we'll be happy. Okay? It goes like this. Once again, consider that picture I drew a moment ago, where I simply consider two-dimensional Minkowski space and draw x and t. I hope this kind of diagram is familiar to you all. If it is, then you will also be familiar with the idea that it is often useful to draw in a pair of light rays to guide your eye with respect to various relativistic effects. And in case you haven't noticed, I have so far in all of my formulae been setting c equal to 1, meaning that I am intrinsically using units of, say, seconds for time and light seconds for position, so that light travels at 1 light second per second. simplifying my story. So because c is 1, if I wish to draw the path of a light ray from the origin, well, the speed is really just the slope, or perhaps the inverse slope. So a light ray is something that travels along a 45-degree line. So let me draw a light ray that passes through the origin. And let me also draw the other light ray that passes through the origin. Okay. Now, my claim is going to be that each of these light rays has the kinds of properties that we normally talk about for black holes. I will therefore take a step forward and call this a horizon. Okay. However, an important property that we will learn here, but which is also true for black holes, is that a given surface only acts like a horizon for certain observers. So in the black hole case, there we go. In the black hole case, I said that a black hole is a property that no information from the inside can come out. So what that means is that for observers who remain outside the black hole, they can learn nothing about the inside. Okay? But of course, suppose that instead of remaining outside, you decide to jump into the black hole. You could do so. Why not? In that case, presumably you could learn about the interior. So the black hole does not say that no observers can learn about the interior, but only that some observers are forbidden to know about the interior. The same is true of this horizon. Because in Minkowski space, there are many observers, say the inertial observers that just go on forever, who, if enough time passes, can make measurements very far away, collect lots of information about Minkowski space, and learn about everything that goes on. But it turns out there are other observers for which this light ray forms this kind of one-way barrier where they cannot see anything beyond it. And let me show you what those are. The simplest example of such an observer is, let's see, what color should I use? I guess the yellow will show up well. The simplest example of such a class of observers are what are known as the uniformly accelerated observers. So imagine not an observer that's sitting out in space, just floating, but imagine instead some observer who is sitting inside of some rocket. Say a rocket with an infinite amount of fuel, just for sake of argument. And that observer turns on the throttle, okay, so that she starts to accelerate forward. And suppose that she sets the rocket so that at every moment the thrust is the same as measured by her. So she feels the same force pushing her forward for all time. Okay? That's what I mean by uniformly accelerated observer. All right. Now let's try to draw the world line of the uniformly accelerated observer here on this diagram. Well, we can guess something about it because, of course, the observer keeps going faster and faster and faster, keeps speeding up, right? But this is special relativity, so we know that the observer will never go faster than the speed of light. Instead, they will only asymptote to the speed of light as more and more time passes. So it should therefore be clear that a world line for uniformly accelerated observer looks something vaguely like this. Goes up and asymptotes toward this world line. Okay? All right. In fact, if that observer had actually always had her rocket on, even in the sort of infinitely distant past, then one can argue that the bottom half of the world line must look the same. Okay? Basically because of time reversal invariance. Okay? If you see that I've chosen this line here, t equals 0, to be a point where the observer has a vertical world line, and therefore 0 velocity. So that says that this problem is an invariant under time reversal, t goes to minus t, and the bottom half of the world line must look the same as the top half. Okay. So here we have a uniformly accelerated observer. And my claim is that as far as this uniformly accelerated observer is concerned, this red line behaves much like a black hole. Okay? So let's just check this. Let's see a few properties. Suppose, for example, our uniformly accelerated observer has a friend that she drops out of her rocket. And suppose the friend sort of wanders down here, tossed out. Actually, let's do it this way. Just for fun, let's drop the friend here. So the friend is just stuck outside the rocket and now has an inertial world line because they're freely falling in space. And then there are several things that might happen. Perhaps the person we dropped has a little rocket engine of their own and can later accelerate and catch up to the rocket. Okay? That might happen. Okay? In that case, well, okay, I'm going to cheat a little bit. We'll come back to the details of this. But in that case, this problem, where one observer does something very simple, the other goes out and undergoes a greater acceleration to catch up, should remind you of the famous twin paradox from special relativity. So you can guess, we'll do a calculation, well, we'll make the calculation more explicit later, but you can guess that what happens is that the green observer does catch up, but records the passage of less time than the one who remained out here. Well, that's one of the phenomena that we mentioned for black holes, right? Here's my example for the black hole. So there's a similarity here. Okay. Let's do something a little bit more extreme. Suppose that we really don't like our friend, and we don't give them a rocket. We just drop them. Okay? Then in case, they will, of course, just move as an inertial observer forever. Okay? So what happens if we now watch our friend as time goes by? Well, if we're watching our friend, this is much like the discussion from George Ellis this morning of watching distant galaxies. Okay? To find out what we see, we have to trace light rays between our friend and us if we're watching our friend through a telescope, because the light has to get from our friend to the telescope. So suppose our friend emits some light rays. They, of course, also move. They have slope 1, because c is 1, so they move at 45-degree lines. And if our friend emits light rays, say, once a day, then we draw little lines that are equally spaced. And you see, you see that there is a last light ray from our friend's world line that will ever reach the accelerated observer. Right? So what we see then is that for everything behind the horizon, for the entire part of the green world line up here, all of those events are, in fact, causally separated from the yellow observer. There is no way in principle for the yellow observer to ever find out what happens to the green observer beyond the horizon, thus qualifying it, thus giving us the legitimate ability to name it a horizon. Okay? In fact, let's think of it this way. Although there are light rays, well, I'll leave it there. Although there are light rays from the green observer that never reach the yellow observer, if I do the opposite problem, if I take an arbitrary point on the yellow world line and trace it back, I will always hit the green observer's world line. So in some sense, some rough sense, the uniformly accelerated observer can always see the green observer, okay? But they only see this set of events. So what happens is they watch the first events pass rapidly, and then as time passes, the new information reaches them more